While the world slides into a global water crisis, nowhere is the pressure more intense than the Middle East. Iran has warned that if shortages continue, parts of Tehran may one day need to be evacuated. Iraq's great rivers now carry barely half their old volume. Across Syria, Turkey and Jordan, fields are turning to dust and aquifers are running dry. But one country has the opposite problem. It has too much water: Israel. On paper, that shouldn't be possible. About 60% of Israel is desert or semi-arid. Rainfall can reach around 1,100 millimeters a year in the far north, but drops to just 25 millimeters in the extreme south. Yet today, it produces roughly 20% more water than it needs. So how did it pull that off? The answer lies in two engineering projects built 6 decades apart. The first, in the 1960s, carved a 130-kilometer artificial river across Israel, lifting water 257 meters from below sea level to the southern desert. The second, starting in the 2000s, turned the Mediterranean into a tap, a desalination network that now supplies about 80% of the country's drinking water. This is the story of how 2 generations of engineering turned one of the driest countries in the region into the only one that doesn't run out of water. And to understand how extraordinary Israel's water transformation is, we need to go back to the 1950s. At that time, the country's population was growing, farms were expanding, and fresh water was critical for survival. But Israel had only one major natural water source, the Sea of Galilee, also known as Lake Kinneret. Everything else? The Negev desert sat in the south. Temperatures there regularly topped 115 degrees Fahrenheit, and weeks could pass without a single drop of rain. Groundwater was limited. So how did a nation survive when most of your land has no water at all? The idea was to create a 130-kilometer artificial water network, moving water from the Sea of Galilee, 213 meters below sea level, all the way south to the parched Negev. It would take 5 years, cost hundreds of millions, and employ over 4,000 workers. They called it the National Water Carrier, a project that would either save the country or bankrupt it trying. Now imagine building a system to carry water from the Sea of Galilee all the way to the southern desert. It sounds simple, but it's not. The first real engineering wall Israel hits is gravity itself. Water entering from the Sea of Galilee sits about 213 meters below sea level. The national distribution network it has to feed into, around 44 meters above. That's a vertical climb of roughly 257 meters, and it starts here at Sapir Pumping Station. Instead of building a normal surface plant, engineers carved Sapir into the side of a mountain above the lake. Water is drawn in through an underwater pipeline several hundred meters long, passes into a 14-meter deep shore reservoir, and then drops down a vertical shaft into a hidden pump hall. Inside that hall, an 80 by 20 meter cavern 21 meters high, sits a bank of giant pump units. Each one combines a vertical intake pump and a horizontal high-pressure pump, with motors rated at more than 30,000 horsepower apiece, roughly 20 megawatts per unit. Together, they push Lake Kinneret's water from minus 213 to plus 44 meters in a single stage. From there, the flow shoots into 3 steel pressure pipes that merge into a 2.2-kilometer pressure main. That pipe carries up to 72,000 cubic meters per hour, about 1.7 million cubic meters per day, into the open Jordan Canal, where gravity finally takes over and carries the water south. Around the pumps, a maze of service tunnels feeds in high-voltage power, controls automatic valves, and, in an emergency, can dump water straight back into the Sea of Galilee to protect the pipeline. The original 3 underground units have been running since 1964, and in the 1990s a 4th above-ground pump was added, so the heart of the national water carrier never has to stop beating. But lifting the water was only half the battle. From there, it had to travel through 86 kilometers of steel pipe. Buried underground, drilled through rock and shifting sand, crossing farmland where every inch had to be restored afterward. Survey teams measured everything to the centimeter, because one small mistake could stop the flow, or worse. burst the pipeline. And yet it worked. By the early 1990s, the national water carrier was supplying about half of Israel's drinking water. At first, around 80% of its flow went to agriculture and only 20% to cities, but over time that balance flipped as the Negev and other dry regions began to be built out. The system became the national lifeline for over 40 years, until Israel faced a new crisis. By the early 2000s, the population had tripled. The carrier alone couldn't supply enough water. On top of that, a series of droughts pushed the Sea of Galilee to its black line, the official level where pumping is supposed to stop to avoid permanent damage to the lake. In 2002, the government made a radical decision: build a chain of huge desalination plants along the Mediterranean and make the sea itself Israel's main water source. The plan called for roughly 300 million cubic meters of desalinated water per year by 2010 and around 500 million by the mid-2010s. Construction moved fast. Ashkelon came online in 2005 with capacity for about 120 million cubic meters a year. Hadera followed in 2009 at roughly 145 million. Then, in 2013, Sorek 1 opened as the largest seawater reverse osmosis plant in the world at the time, designed for around 150 to 234 million cubic meters per year, depending on configuration and upgrades. By the mid-2010s, these plants together were already supplying more than a third of Israel's municipal water demand. Desalination provides most of Israel's drinking water, on the order of 70 to 80% in a typical year. And in 2025, Sorek 2, also known as Be'er Miriam, pushed that even further, adding another 200 million cubic meters a year in a single facility. That one project alone boosts Israel's total desalination capacity by roughly 35% once it's fully ramped up. The winning bid to build and operate Sorek 2 came in at about 1.45 shekels per cubic meter, around US 40 cents, making it one of the cheapest large-scale desalination contracts anywhere in the world. But building a plant is one thing. Making it efficient enough to run at national scale is another. At Sorek 2, the engineering starts offshore. Instead of open intake pipes that suck in fish and debris, the plant draws seawater through subsurface intake wells drilled 20 to 30 meters below the seabed. Sand and rock act as a natural filter, stripping out large particles before the water even reaches the pipes. Inside, the water passes through banks of hollow fiber membranes, each fiber thinner than a human hair, with pores measured in microns. They remove algae, bacteria, and fine sediment, protecting the main reverse osmosis trains from fouling. Then comes the hard part: reverse osmosis. High-pressure pumps ramp the water up to around 60 to 70 bar, similar to the pressure 600 meters below the ocean's surface, and force it through thin film composite membranes with pores around 0.0001 microns wide, about 1/100th the size of a virus. Salt ions, heavy metals, and most dissolved chemicals are left behind. Sorek 2 uses an optimized RO train and modern energy recovery devices to squeeze as much fresh water as possible from each kilowatt hour. The water that comes out of those membranes is almost too pure. It's slightly corrosive. So the plant adds carefully measured amounts of calcium and magnesium, adjusts the pH into a neutral range, disinfects with UV light, and adds a trace of chlorine so it stays safe as it travels hundreds of kilometers through the national network. In total, Sorek 2 can produce roughly 550,000 cubic meters a day. At typical household use of 100 to 200 liters per person per day, that's enough drinking water for between 2.7 and 5.5 million people. Because of this shift to the sea, Israel could finally ease the pressure on its natural lakes and aquifers. In the early 2000s, the country was still pumping around 500 to 513 million cubic meters a year from the Sea of Galilee. By 2018 to 2019, that had fallen to around 25 million cubic meters, a 95% reduction as desalination and conservation took over. And Israel didn't stop at making new water. It also learned to use the same water twice. The Shafdan wastewater treatment plant near Tel Aviv now processes around 400 million litres of sewage every day, sending treated effluent through underground pipelines to irrigate farms in the Negev. Nationwide, about 94% of wastewater is collected and treated, and roughly 87% of that is reused, mostly for agriculture. That's by far the highest reuse rate in the OECD. The next country on the list, Spain, reuses only about 20%. Desalination now supplies most of the drinking water, and recycled effluent covers a huge share of irrigation. Almost every drop in the system does at least 2 jobs before it's allowed to leave. By 2020, the problem had flipped. Desalination plants along the Mediterranean were producing more water than Israel needed in a typical year, even as the Sea of Galilee remained vulnerable to the next big drought. Engineers and planners floated a radical idea. What if desalinated water could be pumped backwards through the national water carrier and into the Sea of Galilee itself? No country had ever tried anything like this at national scale, piping desalinated seawater into a natural freshwater lake as a strategic reserve. Israel would be the first. The National Carrier Flow Reversal project took about 4 years to build and cost roughly 1 billion shekels, around 250 to 300 million US dollars. New pipelines were laid to connect coastal desalination plants such as Hadira and Sorek into the existing carrier. Dozens of kilometers of large-diameter pipe, up to 1.6 to 2 meters wide, were manufactured off-site, hauled on multi-axle trucks and welded together section by section. In open countryside, crews could dig conventional trenches, but along highways and built-up areas, that wasn't an option. Instead, they used horizontal directional drilling, boring tunnels beneath roads, rivers and utilities, and threading the new main through without ever opening the surface. Existing pumping stations designed for downhill flow from the lake to the south had to be rebuilt to push water uphill instead. New high-pressure pumps and backup generators were installed so the system could keep running even if a unit failed or the grid went down. Along the way, new balancing reservoirs were dug to store water during off-peak hours and stabilize pressure. All of it is tied into a central control center that monitors pressure, flow, and water quality in real time. Operators can redirect water or isolate a problem section in minutes. In late 2023, the system was switched on. For the first time, water that started in the Mediterranean Sea was pumped inland, up through the reversed carrier, and into the Sea of Galilee. Initial capacity is about 5,000 cubic meters per hour, with plans to roughly triple that to 15,000 cubic meters per hour as more desalination plants and pumps are added. Today, Israel runs a circular water system like no other. Seawater becomes drinking water. Cities and farms use it. Then 94% of wastewater is collected, treated, and 87% goes straight back to irrigation. Surplus desalinated water now flows backward into the Sea of Galilee, ready for droughts or sharing with Jordan. In just 60 years, a desert became a powerhouse. Regions barren in 1959 now produce 60% of Israel's fruit and vegetable exports. But the story isn't over. In northern Israel, the next piece of the puzzle is already under construction. The Western Galilee Desalination Plant is a roughly $440 million project designed to produce around 100 million cubic meters of water per year. And it's scheduled to start operating around 2026 to 2027. It will be the first major seawater desalination plant in the north, feeding cities like Haifa and the Western Galilee directly from the Mediterranean rather than relying on water pumped from the Sea of Galilee. But even that won't be enough. Recent studies suggest that by 2065, Israel may need up to 3.7 billion cubic meters of desalinated water every year to meet demand under high population and climate stress scenarios, roughly 5 to 6 times its 2020 output. One analysis estimates that reaching those levels could require building around 30 new desalination units over the coming decades, on top of today's plants. Several more projects on the scale of Sorek 2, and then several more after that. Think back to 1959. Israel faced what seemed impossible, building a nation in a desert with almost no water. By 1964, they had constructed a river that didn't exist. By 2025, the country had built one of the world's most advanced desalination networks. Sometimes, engineering doesn't just solve the problem. It changes the rules of the game. Now you tell us, what part of Israel's water story surprised you the most? Drop your thoughts in the comments, and if you want more Megaproject stories like this, subscribe to Megabuilds and stay tuned for the next deep dive.